Hello again, folks, and this is going to be my final stream for 2020. So this year I did Advent of Code. This is now my 6th year of having completed Advent of Code, and I really enjoyed it. There is one puzzle that I glossed over that I solved in a very cheesy way, and today we're going to be going back to solve that puzzle. And then after that, we're going to go through all 25 days and summarize what each puzzle was about and what I learned. So I hope that other people enjoyed my streaming this year. This is now, I think, my 3rd or 4th year of having done this. And it's been a lot of fun sharing this with all of you, and I hope it's maybe inspired you to do Advent of Code yourself. So with that, let's go ahead and go over to my screen. So this is what a completed Advent calendar looks like. But if I open a new incognito tab, what you'll be able to see is this is what it looks like when you haven't completed it. You'll just see the empty world map. So you can see here that I've completed all 25 of the days. But there is obviously a little bit of stuff that needs to happen here. So specifically, what happened with day 20 was this was kind of the flagship puzzle of this year. This was the most infamous puzzle. This is the one where Eric is selling T-shirts, and you're supposed to find these sea monster things in a pixel image. But it comes with an extra twist. And the extra twist is you are not given the space to search entirely on its own. Instead, what you are given is you are given tiles that have been potentially flipped, rotated, any number of things, and that introduces a fair bit of complication. So what this is supposed to look like, for instance, is it's supposed to look something like this, and you're supposed to be able to figure out based off of the borders what goes with what, and then reassemble. And unfortunately, let us say that I did not actually do that to solve. This year, in order to solve and find the sea monsters, I actually didn't find the sea monsters. I just guessed that there were going to be 30 sea monsters, and without finding the locations. And that was cheating a little bit. It did get me the stars. It did let me get the day 25 completion as well. But I feel like I cheated myself a little bit, so I want to go back and do it. So let's quickly go and have a look at what my puzzle input looks like. So my puzzle input looks something like this. So it's got a bunch of 10 by 10 tiles. But we can also see that I pulled down their sample input, which is only 9 10 by 10 tiles. There are a lot more tiles in my particular input that is designed to be solved the smart way. Oh, the other thing that I should mention is I started off this year streaming on an AMD 64 processor. I switched midway through this year to streaming on my ARM 64 machine. And as of today, we are back on an AMD 64 machine that has been more or less rebuilt from the ground up. New motherboard, new CPU, new graphics card. So I have a Ryzen 5600X, and I've got a 6800 AMD Radeon GPU in here. It's a little bit different in terms of its performance characteristics. Hopefully it won't need to run for super long. But like you'll see here that it is, it's executing on 12 cores. Except for it's not actually 12 cores. It's 6 actual cores and 12 hyperthreads. So the performance is going to be a little bit slower in terms of parallelism, but it's going to be faster, much faster in terms of maximum clock rate and IPC. So that's what's going on with my computer. Is I broke my AMD 64 machine trying to upgrade it. The motherboard was bad. So I wound up having to, in the course of trying to put in these spicy parts, as Twitch chat is commenting, I wound up having to switch computers entirely because it was not going to work to stream from a completely broken and dead motherboard. All right. So, did I give up an arm and a leg? Kind of. I paid a scalper about 10% over MSRP in Canada. which is not bad. It was not a 30 or 40 or 50% premium. It was just 10%, which, my time is value. My vacation time is value. And I find it fun to build computers. I do not necessarily find it fun to press F5 on web pages or stand physically in line in a store in the middle of COVID. All right, so let's recap what happened on day 20. And yay, thanks Idlestar, astronomer. That is really good that you could catch this live. Because most of my streams have been right at Puzzle Unlock, but obviously there are no more Puzzle Unlocks this year. So it means that we get to do this during other hours. Okay, so hey A9. Here's what happened when I was solving this on day 20 of the real puzzle challenge. On day 20 of the real challenge, what happened was I did a really, really complicated and buggy and potentially broken thing of keeping track of which tiles were flipped which way, and of when I asked to access a particular pixel, fetching the tile from that particular pixel position and flipping it on the fly. In retrospect, this was a really, really bad idea. I should not have done this. So what I'm going to do is I'm going to completely gut my day 20 solution, and I'm going to redo it from the ground up. I believe that the better way to do this instead is if you look at these input tiles here, what you'll see is that you can only use each tile once, but there is nothing stopping you from generating the rotations of the tile in advance, and then just once you find a tile position that matches for that tile, ruling out all of the duplicates of that tile that you've created. So I think it'll be easier, instead of kind of checking its rotation, rotating the pieces every single time. Flip, yes, you can flip as well. Basically, instead of flipping on the fly every single time, why not just generate 8 copies of each of these, right? So the original rotation plus 4 rotations plus flip plus the 4 rotations of that. And then that just makes that a lot simpler, because then at the end, if you solve that, you're just left with a grid that works perfectly well. So that is my working hypothesis of how we make this problem a little bit more tractable and a little bit less error prone. So that's what I'm going to be doing. The other thing that I saw, I have spoilered myself, I've seen what other people have done, is I do see that some people, when they were solving, they wound up kind of doing a graph search to try to piece together what potential combinations might go where. So they start from one piece and then work out what can connect up, down, left, right, etc. And they'd sometimes have to backtrack. I do not believe I need to do that. My belief is if I go around in a spiral pattern, so I start from one corner because I know what the corners are, and I just iterate around looking for things that have a edge that doesn't match any other edge, so therefore they must be against the side of the board. If I look for, then that means I always have a constraint of at least 2 sides to match on. And I believe that these inputs are constructed carefully so that you don't have to guess, even though there are duplicates of each individual side. If you have at least 2 sides that are required to match, my belief is that you can just go around in a spiral pattern, and that you will successfully be able to solve without having to potentially enter an incorrect tile placement and then have to back it out. So that's what I'm going to be working with. And then finally, at the end of this, once I have reassembled the board, I believe that I could choose to flip the board around and look for sea monsters, or I could flip the sea monster around and look for that inside of the pattern. It doesn't really matter. So that's what I'm going to do today, is I'm going to gut all of this. Anthony Wright's code and A9 are talking about how I solved this the wrong way. The hack that I did last time, I'm sure someone will have the clips.twitch.tv. If you look at this clip here, it's the moment that I guessed it exactly correctly, because I was able to calculate the roughness based off of the number of set pixels, and then subtract, I think, there are 15 pixels per sea monster, so I guessed, 15 pixels per sea monster, 30 sea monsters, just like take off 450 from the number of set bits, and it was correct on the first try. So, yeah, I definitely cheated myself here. All right, let's go ahead and get going here. So we're going to remove this, and we're also going to remove this. So my belief is, once we know what goes where, we can then construct everything fine. Okay. So this is just really, really straightforward now, because now I can always assume that I already have a pre-rotated mosaic. So that simplifies that and lets me delete a bunch of code, which feels pretty good. I also think, yeah, so that's fine. So we'll look for the sea monster at each position. I think that code more or less is fine. So here, I no longer have the notion of a rotated piece, because I just get the edges out of it regardless of what it is. Okay, so the cropping function is still exactly the same. The count function is still exactly the same. That doesn't matter with regard to the rotation. The tile edging needs to change. Oh, in fact, yeah, that's already been done. So I already have something to be able to handle flipping edges around without having to read them in reverse bit order. So if you remember my stream the last time, oh, Anthony writes code. Here's the even funnier thing. I could have done the sea monster guessing trick by, summing up all the hashes and subtracting 450. I could have guessed that the instant I unlocked part 2. Like, I could have been done with this in less than 45 minutes, and I would have placed, like, very, very high on the leaderboard. I did not do that, because I tried to solve it the right way first and only cheated when I got frustrated. But I'm feeling a lot less frustrated today. Okay, so if you remember, this thing here. This thing here represents one potential puzzle piece, right? So it's got a plus side, it's got a minus side, and it's got kind of the XY coordinates of row and column. And it can be rotated 4 different ways. And it can be flipped and then rotated 4 different ways. Yeah, I can totally understand why you didn't solve it that night in the Heroics code, seriously. Okay. So, we have standardized on the edge cardinality. Not that it actually matters now, but the edge cardinality is set up so that a piece matches if the edge reading exactly matches the next edge reading. So if I have a left that matches the right after being flipped, then it means that, yeah. So any edge should correspond after being flipped in order for it to be the same edge. All right. Oh, actually, let's see this. I do need these constants still because they define the order in which the edges are stored. So that is still, that goes here. All right, let's just quickly format this. Yes, Anthony, I have seen Babby. I look forward to using Babby, but I didn't want to learn it during the year in which I was doing streaming at the same time. But now that the streaming year is over, I probably for Advent of Code, I probably will potentially try out Babby. All right, cool. Let's see. So, all this code for part A is good. But now we need to do now we need to construct my virtual tiles, and then we need to start being able to do the search. So the first thing I need to do is I need to do something to support performing a flip on a rotation and a flip on a tile. Which will return, in turn, a new tile. And then I also need to create a function that operates on a tile that will perform a clockwise rotation. And then we'll be in good shape. Okay, so the flip case is relatively easy. You have to pick an axis, any axis, it doesn't matter. So I will choose to flip on the, because these are encoded as a bool array, because the amount of memory used here doesn't really matter. I could use bit array, but it becomes more challenging to read the code of. So I'm just going to, in this case, I'm going to flip it on the x-axis in order to make it so that I just reverse the order in which I read the order in which I read the rows, rather than having to, inside of each row, reverse the order of columns. And in fact, I believe this means that I could technically share the same inner array, but it's, on the other hand, it's kind of sloppy to do that, so I am going to actually clone it. Okay, so how am I constructing a new tile here? So a new tile is being constructed do I ever run make? Fascinating. I do not seem to ever run make on the cropped. Oh, the reason that I do that, I think, is because if you append to a nil array, yeah, yeah, I don't have to worry about that, because when you define this, because it's not a slice, it's a fixed width array, it's automatically 0 initialized. That is really, really convenient. Okay, great. So we're going to define our return value, which is all pretty straightforward. In fact, that's going to be the same here. All right. So ret of 10 minus r is going to be row. 10 minus r? No, it's going to be 9 minus r. This tripped me up before because it's 0 indexed, so therefore it needs to go from 9 to 9 to 0 rather than from 10 to 1. Okay. Good, good. Now, how do I handle the clockwise rotation? that is going to be the only slightly tricky bit. But fortunately, I've got a piece of paper here that details exactly how this is supposed to work. So let's see. Here, we need to construct this manually. Instead of just instantiating row by row, we need to actually copy individual bit by bit. There quite likely is a package that will flip the indices when reading an array. However, for the purposes of teaching myself useful math, I have historically not, in general, made a habit of using third-party libraries aside from anything that is in the language's standard library. If it's in the language's standard library, I'll use it. Otherwise, I consider it something that I potentially want to learn to do myself. All right, so we're going to range over the indices. So here, let's see. If I've rotated, then my spouse is home. The dog is a little bit excited to see her. Okay, so if I rotate without flipping, then what happens here is the row and column reverse themselves, and also, I believe one of them gets flipped in the reading order. So if I'm trying to read the value at row 0, column 0 of the rotated tile, then I believe the new column value is still going to be, if I'm interested in row 0, column 0, I wind up getting row max minus C. And then, yep, okay. I think this is correct. So now, let's see if we can handle the rest of this. And my spouse has also got me Kleenex because it is the winter and my nose is stuffy. Hi, Flurry. You're a dog. Do you want to say hi, Flurry? All right. Flurry, go say hi. Come on, let's say hi to my streaming friends. Oh. See? Look. That's dog. She's not very happy with me. Okay, off you go. Go see your other mom. Go see your other mom. Every single other day that I was streaming during this December, she was already upstairs, sleeping on the floor of my spouse's bed, but not today. She's awake and she's up. Okay. So let us see this. So traverse is fine, except for we no longer need this logic. Yep, okay. So let's go ahead here, I think. And we're going to start over here, I think. So we need to construct each of these. So... Oh, we no longer have a notion of a rotated piece either. Instead, a mosaic is just a collection of tiles now. Okay. Where were we? We were here. We were constructing the mosaic. Let's see, the tile itself doesn't need to be initialized. But we do need to traverse these out of order, so we may as well define this. In fact, yeah. I think that's fine. Okay. So now, this can just map directly to the tile. So this is just going to be that, I think. That's correct. Yeah, it's a map from int to tile. Okay. Great. So now we need a map from tile to int to state which original tile it was. Okay. So first insert the base rotation. All right. All right. In fact, actually, we can do it this way. This is a little bit cleaner. Yeah, this is going to be cleaner. I want to do this twice. Okay. So we are going to do this. And then at the end of this, we're going to perform a flip. What does dog have to say? Okay. So I think that will automatically populate all 8 of the rotations into the map, and it is storable. Because a tile is a fixed bool array of fixed width, I believe that this will work. Golang understands how to use as map keys anything that is serializable in a fixed fashion and contains no pointers. All right. Oh, wait. This needs to be 4. There we go. That is more reasonable now. Okay. Great. So now, instead of passing tiles to traverse, we pass all tiles. And don't need this piece of debugging. And over here, we're going to go ahead and so this is the same thing. How do I handle flipping the mosaic? Oh, I see how to flip the mosaic. If I flip the mosaic, each thing in the mosaic changes places, and I believe, yeah, okay. We'll deal with that in 1 second. Let's just make sure that we can successfully pattern match. Okay, so traverse is a map from tile to int now. So mosaic I think that works. Okay. Oh, dot edges. Okay, that seems fine. Okay, that logic is all fine. These get swapped. All right, so let's try running this and see what happens. I'm very, very curious what happens now. Line 247. Oh, range space tiles. Let's run it on the sample input real fast. So we've got some compile errors to fix, which is not a giant deal. Okay, line 40. These are just set. Oh, there's no longer tile ID. This is instead just literally this value. So we'll do it that way. All right, getting there. Line 250. this is flip X. Why is this taking a... Oh, int and bool, right. Because this now expects to operate on... This should now expect to operate just on the mosaic itself. It no longer needs the map of tiles because it is itself just a listing of the pixels. All right. Same deal. So now, this is just going to be, okay, that's simpler. Oh no, that can't be simpler. That still needs to be this. How do we handle this? I guess we handle operating on the mosaic. The mosaic dimensions are always going to be 10 times there. Okay, that should work. And this becomes R and R here. Oh, and this is the number of rows in the... Okay. Getting there. Pixel at chord. Again, we're just reading it directly. We're no longer using the layer of indirection of what's been rotated and what's not been. Getting there. Line 60. Oh, same fix. Oh, I see. The other fix that I can apply here is just... in fact, these are now 8 and 8, I believe. Remove the borders 1, 2, 3, 4, 5, 6, 7, 8. Yep, that's correct. We'll do this for consistency, and we'll get rid of this. Okay, that is so much cleaner and easier to read now. Oh my goodness. That makes me feel positive about having done this simplification already. It turns out that there is no feeling more satisfying than deleting code. There really is not. Okay, 273. Yep. And now over here, all right, so I think that should, something like that should work. Yep, so I need to define what rot CW and flip are on mosaic. And a mosaic could be a variable width. Okay, so we're going to have to watch out for that, but that's fine. So now we write code that is very, very similar to what we did for tile. So in fact, I'm just going to go and copy that code because I know that it's almost the same. And we'll interleave it. So that goes away. And this goes in here. Okay. But there is a caveat here. We need to so these are all similar, but with one difference. If I have a stack of these tiles, something like this, and then I rotate, what happens is each tile itself is rotated, and then they're rearranged as well. Okay. So a mosaic is a the mosaic operates on on raw values, yes? Yeah, a mosaic is a set of tiles. Okay. Okay, because it's a slice, I'm going to do it this way. All right, just do it, and then okay, so here we need to get, wait, I have these backwards. That's better. I was a little bit worried about that. Okay. So if I'm flipping along the x-axis, that means that I am flipping each element, and then I'm the order of each element. So that's going to be that's correct. I think this should work. Okay, some more logic here. Okay. I do believe this does it. All right. Oh. Of course, going requires you to store the result of append as well. Okay, getting there. 307. It's good. And 8 all tiles. Okay. This one is just length of m, length of m index 0. Yep. That looks good. Okay. Yes, we don't care about the direction anymore because we've already pre-rotated these. It doesn't actually matter. Okay. So does this value here match that still? Yes. What about if I run it on that? Does it still match my original part A answer? Yes, it does. Good. Okay. So now we have code that compiles. And it compiles, and my previous code never worked for part B anyways. I'm going to go ahead and check this in. Because I always like being able to go back in time when I'm coding, because I often will accidentally delete code that I meant not to delete, etc. So we'll go ahead and push that out. Okay. So now let's run and see what it complains about. It says failed to traverse right from what should have been top left. Why does it fail to... Okay, so let's print a couple of these. I'm curious what the, let's print the count, let's print the length of all tiles, and let's print the length of tiles. Just to check, I should see... Okay, there are 144 original tiles. 144 times 8 is 1152. Yep, okay, so that's correct. And they're all unique tiles because otherwise Go would detect that they're not unique. Okay. So let us print as we place things. Oh, and also we need to populate as well. Oh, I see what happened. Okay. That was silly. We need to set what the next edge is. I accidentally deleted that when I refactored. Okay. Yes. We also don't need to check all of the edges because we know that it has to continue the pattern. So that's also an optimization we can make. Okay. Okay. Yep. So loose.flip is edges of I'm going to define an opposite really fast. Oh no, but I can't define an opposite on the iota, which is annoying. Okay. That's fine. I understand what I needed to do here. Okay. So it's the direction. And now we need to save this tile. So m of row of coal will be t. Okay, let's try that. Almost there. Oh. Ha! Excellent. That almost works. That's really exciting. Except for I'm generating really, really verbose debug output. Where am I printing now? Okay, that's fine. I think debug is set to false. Why is this printing that? Oh, no, that shouldn't be printing because debug is off. Okay. Okay, well, let's look at where this error is happening. This error is happening at line 36. Oh, that means it's getting that far already. Excellent, excellent, excellent. Oh, I see my problem. So I need to see where I'm first defining the mosaic. And is this actually doing the right thing? Yeah, that's correct. Var line. Okay, so that's not where the problem is. Line 36. Mosaic row. Mosaic column. Why am I asking it for a row and column that's out of bounds? What am I calling it with? Yeah, I should never be calling it... Okay, so my logic here is busted. column plus the length of the sea monster must always be less than, each of these is 8 wide. That should work. I don't understand why that works. It doesn't work. Okay. Well, we're at least getting further. So we did, in fact, successfully match. Where is that print coming from then? Oh, that print is coming here. Okay, yeah, that's unnecessarily verbose. Okay, so now let's run that. Okay, good. Let's just print now the debugging information of what are the coordinates that I'm checking. Okay. So it tries to go up to 95, which would normally be fine. So it successfully fetched up to 95 here. But why does it fail there? Oh, because I'm going off the end. 6.5. Huh. That's interesting. So which index is out of range here? Wait. Oh. Is that it? Is that really it? Yeah, that's okay, that's better. I was constructing an absurdly wide sea monster that was 1 pixel tall, and okay, yep, got it. Okay, now we're erroring at a different place, line 59. Okay, so my rotation is now busted, which is easy enough. Well, this is getting further along than I ever got with my like 3 hours of working on the original day of. So I am pretty happy to have made a lot more progress in 1 hour rewriting this. Okay, so index out of range at line 59. M. Yeah, seriously, like, I think I woke up the morning after I solved it the cheesy way, knowing exactly what I had to do. But I was so far behind, right? Like, I was like, I need to stream every single day to keep on top of Advent of Code. Like, I didn't have room to squeeze in, 3 hours or 5 hours or like an unbounded number of hours into the rest of my streaming schedule up until the 25th. So I was like, you know what? I know what to do on day 21 to solve day 20. I'm not going to do it. I'm going to wait until the wrap-up stream and do it properly. Okay. I'm going to see our rot CW. That should be fine. Why is it nil pointer erroring? Oh, it's not nil pointer erroring. It's saying index out of range. That's very different. Why is C less than what the hell? Oh, it iterated to -1? What? Yeah. Okay. I see what's happened here. The mosaic should always be square. So this number should always count. I do not like this. Something weird is happening here. Why is this not terminating? Okay. Let's just make sure that's all copacetic here. Okay, yep, those are 3 by 3. And that is all 12 by 12, so that should be fine. Oh, because it's not 9 minus. This value here. Yeah, okay. Now I understand what's happening. That's gone wrong here. So this is going to be length. This has to be number of columns. So okay. There we go. That's better. Line 59. Oh. -1 minus C. Settle off by 1 errors to get you every time. Line 47 now is wrong. Yep, 9 minus 1 minus R. Same deal there. Oh, and not just that, it's there we go. Just bad constants. Yeah, because we know here that this is 10 minus 1, because each tile has a fixed number, but the mosaic has a different number. Okay. All right. So now that looks good. So now we are successfully assembling part of the mosaic. So now let's go ahead and assemble the entire mosaic. So the first thing we're going to need to do is to avoid the dead ending I talked about. In order to avoid dead ending, we need to enforce the constraints. Yes, we do. Where is this? Wait. Habitat's roughness is 273. So that actually already returned the correct result. Okay, so I'm already getting the correct result here. I actually don't need to change any of my code. Fascinating. Okay. So where is 2130 coming from? Oh, I know where it's coming from. 2130 minus 450 is 1680. Okay. So I am assembling this correctly now. I didn't need to do the spiral pattern. The only thing that's wrong now is looking for the sea monster. So let's just verify that that's what's going on. Okay. All right, so that one does in fact generate the correct output. And yep, we're failing to detect any sea monsters. Okay, well that's progress. So my code now works on the example code. So let's go ahead and check that in. And push it up to the server. And then we'll have a look at now let us have a look at why we are failing to detect any monsters. And I suspect the answer is indeed right where I was working here, which is we are failing to enforce additional constraints. So we need to check for every existing tile. Wait, that's going to generate 8 things around it, including the diagonals. I don't need to do that. Okay, so I need a function to check edges on a mosaic. In fact, I don't think we need loose anymore either, because the mosaic is already populated. We're going to do it this way. That should look fine. Great. So okay. All right. All right. All right, so this will check my left edge against some other piece's right edge. What are these called? These are called top, right, bottom, and left. Great. Okay. So yeah, so this now, we don't need flip. We do need check fit. Okay. All right, that should do it. Mosaic check fit T in the position row and col. Yep, that works. All right. Okay. So if it is if C plus 1 is greater than or equal to don't want to go off the edge. -1, that's annoying to read, but I'll roll with it. Ah. Yeah, okay, that's good. Where is this code that I was in the middle of writing? Ah, check fit, okay. So we want to always say it's fine if we're off the edge of the map, at least for now. Okay. Top is the same story except for it's R. Over here, it's greater than or equal to. Oh. Okay, that's why I did that, because then that works out to that. Okay. And that's a plus. Okay. dir plus 2% 4. All right. This is going to be another tile. Okay, something like this should work, I think. And then we just have to adjust these things. Okay. R plus 1. C minus 1 R and C plus 1 R. So now, other tile is going to be, what is the other tile here going to be? The other tile here is going to be mosaic index R, C. If other tile dot edges index T edges R, or T edges dir. Flip. Okay. Let's run that and see what happens. Odor is just that. Yep, we don't need loose anymore. Okay, so now we've regressed a little bit, which is fine. Village first right from what should be top left. So what possibilities are we trying now? Oh, I didn't check the possibility that was a nil tile. Of course. So I was expecting an edge to be all zeros, and of course that doesn't work. If another tile is an empty tile, return true. 346. Okay, that works now. Now let's try running it on my real input. Failed to detect monsters despite rotating and flipping. Okay, so now I am enforcing all of the sides, and yet I'm failing to detect monsters. Have I used all of the pieces? Just make sure that that's not getting messed up. Run it again. Yep, so we have used all 144 pieces, and now we are verifying that they fit on all of the sides. So now there is just a problem with my sea monster detection and nothing else. Well, that narrows it down. And the thing is that the sea monster detection worked. Yes, the sea monster detection worked on the example, which is fascinating. Okay. So what's going on with my find monsters? Oh. That feels really bad. That should solve it. There we go. It works. Yay! Oh my god. That feels so good. Okay. Solved it in 90 minutes. I consider that to be a pretty good accomplishment. All right. Let's go ahead and clean this up. So first of all, let's go ahead and group all of the code that is a class function in one place. So we will, where is this code hiding? Okay, check single edge. All of these things should go with mosaic up here. All right, let's go ahead and rearrange the stuff that deals with tiles and move it up to be up with talking about tiles here. The edges are still up here. And defining what a sea monster is should go here. Still works. Okay. That makes me happy. I don't know why other people needed to do a search and backtrack, because I managed to solve this without needing to do that. Okay, and then, yes, I'm just, oh, I can simplify this too. Do this as well. We're going right, so that should correspond to number of columns. Each column depth of count is not equal to probably have an off by 1 here. Is that correct? Yep. Okay, now that's correct. Good. So that logic is more readable. Going to take out this debug code here. Okay, that number of corners and sides found, that's still fine. That's not too verbose. In fact, yeah, I don't need my debug flag anymore at all. All right, and then the other thing that I need to do to clean this up really quick is, let's clean this up by defining oh, this is readable enough. I could define a separate function to construct all tile rotations, but I'm probably not going to bother. You can see what I'm doing. Okay. Just make sure that continues to work, which it does. Yep, 273. Okay. tell I'm excited because I used exclamation marks in my commit message. All right. I'm going to take a quick break just to get a little bit of water. I'll be back in 60 seconds, and then we'll go ahead and do the wrap-up and review what every day was like and what I learned from each day. And then after that, I will bid you all a Happy New Year and middle finger to 2020, seriously. All right, so welcome back, folks. It is now time to review what every day's puzzle was and how I solved it. So, just to recap the plot of this year, the plot of this year is that you're supposed to get to your vacation on an island and pay for your hotel deposit with 50 stars. And you start at the North Pole, and you take a bunch of flights. It looks like you're going to get to your destination on time. And then suddenly a storm comes and blows your ferry off of course, and now you can no longer make it to your vacation without going through a bunch of stuff. So that's why there's this little backtracking in the puzzle outline. I thought the story is kind of cute. I really liked it. Although it was kind of interesting to see, like, why is there skipping in the order? Oh, I bet Eric's doing something sneaky. So in day one, you're given a list of numbers, and you're asked to find which of them wind up having a sum that adds to 2020, and then you multiply it together in order to make sure that you've solved it correctly. So it's kind of a checksum. A lot of Eric's puzzles kind of have this checksum mechanic, so that way you can't guess it randomly. So here, instead of asking for two numbers, he just asks for their product. And it's a pretty straightforward iteration, with the caveat that in order to reduce the complexity a little bit, the thing that you can do to move a little bit faster instead of going through 2020 time, or like, billions instead of millions of combinations, is if you bust, as in blackjack, then obviously you can go ahead and check the next set of combinations rather than continue going over if you've already busted. So that's what happened in day one. Day two was a puzzle where you had to do input matching and mangling. Really not much numerics needed, just, iterating through and counting the number of characters in each each input, and then counting what your passwords were. So again, like, days 1 and 2, can you learn to use your language to parse things? Can you learn to use your language to do basic arithmetic? Day 3 starts getting to the point of introducing modular arithmetic, because you start having input patterns that need to repeat. The one thing that threw me off here was that I accidentally, in my simulation, I was always going down by one line every time, and when I started needing to go down by 2 every time, I didn't correctly handle that in my simulation. But yeah, basically you needed to use a repeating pattern to the right in order to get to the end. Okay, day number 4. Day number 4 was again a input manipulation puzzle. So basically, hey, can you parse this list of things, and can you convert all of these constraints that are expressed in prose into code? So again, like, not much complicated algorithmic, just a lot of flavor about passport readers. In day number 6, this was basically handling bit arrays, and specifically handling, you know, are you able to handle, wait, oh, we skipped over day 5. I accidentally skipped day 5. Okay, day 5, the title was a clue, binary boarding, to either do a binary search or to just interpret the number as a binary number. So you were given forward, back, or FB to refer to, you know, forward, you know, go halfway then, and then halfway backwards, and halfway forwards, and halfway backwards. Turns out that's just how base 2 arithmetic works. So I was able to just really quickly parse things from most significant to least significant bit, and go ahead and iterate through. Okay, day number 6. So day number 6 was manipulation of bit sets. So again, you know, keeping track of which things have you seen, how many things have you seen where at least one person answered a thing or where everyone answered a thing. Day number 7 started to get a little. Day number 7 was this first kind of somewhat algorithmically interesting problem, because of the fact that you needed to traverse a tree, not a graph, at least. You know, so there wasn't the potential of cycles. But you needed to go through and figure out, either using a recursive approach or using a work queue approach. You needed to determine what the total sum was, essentially, of all of the nodes in a tree multiplied out. So that's what it was about. The flavor text is super funny. There are a lot of really funny illustrations. The illustrations, fan art illustrations, happened this year. They're on #AdventOfCode. If you do a media search, it's amazing. I really loved all of the fan art this year. Day number 8. So this one was the only VM problem this year. Unlike last year, 2019, where every other problem was a virtual machine problem, this year there was only one virtual machine problem. So I wrote a bunch of this code expecting it to be reused, and it was not in fact reused. Every single year, I believe, so far has featured a VM problem, but last year was the only one that made half of the problems about VMs. So I talked about this in depth in my computer science bootcamp at the start of this year's Advent of Code, so I'm not going to cover exactly what this did, aside from saying that this was a pretty straightforward VM, with the caveat that you had to be able to change instructions, not on the fly, so there was no kind of self-manipulating code, but you did have to try changing each instruction and see whether it made the program run correctly. Day number 9. So day number 9 had this idea of adding up numbers in order to check to see which numbers might be kind of Fibonacci-like. So again, this is pretty straightforward in that you just keep a rolling sum. The one challenge that people encountered, I believe, was that some people wind up doing what's called the fence painting algorithm, where you start from point A and you iterate to here and you're like, nope, it didn't work. And instead of going, okay, I'm just going to add one more number and progress a little bit further and check, they're starting all over from the beginning and adding up all the numbers, right? So that transforms an algorithm that is linear in time to an algorithm that is n² in time, and that can get very expensive. But that was the only real trick to day number 9. All right, so let's go to day number 10. In day number 10, this one was the first problem that a lot of people fell down on. In fact, I'm going to use this view because I think it's easier for illustrating relative difficulty of puzzles, as well as not having to skip around and look for it up and down the list. So in day number 10, you'll notice this is the first puzzle where a lot of people completed part A, but only a fifth of the people who started and finished part A managed to. About a fifth of people completed part A but did not complete part B. Here's why. The reason is that you are asked first to make sure that you understand the problem, right? Like, how many did you parse your input correctly? And then secondly, after that, you're asked how many different possible combinations of walks along this list that follow the rules exist. And the trick that you were supposed to find was that you don't have to walk the list from start to finish every time. And instead, you can cache your results or memorize them along the way in order to avoid duplicate computation. So this was the first puzzle where you had to do that, where you had to memorize in order for your solution to run in reasonable time. Otherwise, it would literally take months or years to complete. So some people, about a fifth of people, did not manage to figure out memorization or look it up, and therefore they got stuck. Okay, day number 11. So in day number 11, this is the first kind of state machine puzzle, or kind of Conway rules puzzle, in which the behavior of a given node winds up varying over time. So what I wound up doing for this year was I constructed a coordinate system and just had a map. So if a bit was set in the map, it meant that the C was occupied. If it was not set, then it meant the C was not occupied. And if the item was missing from the map entirely, then it was not a valid tile to iterate over. So after that, it's a pretty straightforward matter of simulating using each rule, simulating each chair. For the second part, you're asked to not just check your immediate neighbors, but also check anything in line of sight until you run off the edge of the grid. It's possible to slightly optimize by storing the list of who's in your line of sight, so you don't have to recompute it in every tick. Otherwise, it's basically adapting your state machine from part A. Okay, so that was day number 11. Let's look at day number 12. So for day number 12, this is where you're like, oh no, we ran into the storm, we're not going to get to our vacation on time. So this one really, really threw me, I think, because I wound up overcomplicating it a little. But basically, this requires you to move your ship around a coordinate plane. A lot of people did really, really cool stuff with like the turtles, or like the classical thing that people teach computer science and robotics with. So basically, you're asked, depending upon whether it's part A or part B, to either just follow the list of instructions and, turn, rotate, move forward, move back, or just move in a specific cardinal direction. But for part B, instead of changing your cardinal directions, the action that you were manipulating was changing how much you moved at each step, instead of just giving you an absolute number to move by each step. Okay, day 13. In day 13, this was the first puzzle that really, really got mathy, because you needed to find something that essentially involved calculating least common multiples repeatedly. So if you got the mathematical trick, it was very, very fast. If you didn't get the mathematical trick, you were going to bang your head against the wall for a while. And in fact, again, you can see, of day 13, about a quarter of people never completed day 13 who started and got day 13A done. So let's review what happened here and why. A lot of people started naively searching, just iterating each individual possibility one at a time. However, as you can see here from my solution at least, right, like there are not just millions, there are not just billions, there are not just trillions, right? There are hundreds of trillions of possibilities. So instead of checking them one at a time, the thing that I discovered when I thought about it was that if you had a partial solution to just 2 bus lines, you could iterate that and solve it for 3 bus lines. And if you had a solution for 3 bus lines, you could solve it with 4, right? So that realization that you could use an iterative process to solve one additional constraint at a time was what I used to very, very quickly solve it on the day of. Okay, day number 14. Day number 14 was a day that C programmers loved and everyone else hated, because it involved a lot of bit mask manipulation. And specifically, it involved needing to not just set individual memory addresses, but set individual memory addresses with modified values according to the current bit mask, or even worse, probabilistically, or kind of storing combinations of values, such that you have to check all possible values. So that was particularly interesting. Okay, day number 15. So for day number 15, this one was a mathematical sequence construction where you needed to basically iterate through a list of things, and it was possible that you had a really, really slow implementation that would work on part A but would not work on part B. I believe I did not wind up stumbling into this because I just implemented it correctly to begin with. So the optimization that you needed to make was to keep track of not just a list of every number you had seen before, but instead storing the turn number on which you saw each previously seen number. So if you stored that map of number spoken to turn number, you didn't need to store the sequence of every number ever spoken, and you didn't need to linearly search through in order to find every number. So a lot of people, again, fence painted there where they needed to instead use a hash map. Okay. Day number 16. So here you are asked to find n known values. It was a constraint solving problem. You were asked essentially, given a list of fields that were ambiguous, but one of which was fixed for sure, right? So this was set up so that you were not sure if you knew that, A mapped to B, and then you knew that 1 could map to either A or B, right? And then you knew that 2 could map to A, B, or C, right? So you were able to eliminate things one at a time and then reduce them from the set of possibilities and be able to deterministically solve this. So this was a pretty straightforward introduction to constraint solving, except for without ambiguity, just with straightforward elimination process. So we also see that in logic puzzles. If you like logic puzzles, day 16 was kind of the day for you, except for you didn't have to guess and check possibilities. Okay, day 17, Conway cubes, amazingly fun. I really loved this one. So day 17 was a twist on Conway's Game of Life, except for instead of happening in 2 dimensions, it happens in 3 dimensions at first, and then escalates to solving in 4 dimensions. Some people got really, really tripped up by this, because their logic was excessively complex, I would say, and therefore that they didn't abstract on dimensions, or worse, that they kind of needed to manually calculate a bunch of possibilities. The solution that I used here was, so it kind of is a further iteration of I think it was what, day 8, no, which day was it? Whichever day it was that had the, that had the seat rearrangement, where people were waiting. Oh, right. I think that was day 8. Wow, I'm really, really confused here. Ah, yes. It's a variation of day 11. Right? If you solved day 11, you were already familiar with this idea of state machines and kind of having to modify a node's state based off of the previous state and based off of any chairs that were adjacent nearby. The difference between that day and day 17 is that instead of there being a finite number of chairs, there are potentially infinitely many chairs, right? There are potentially infinitely many cubes that could be activated. The trick here is if you do not use an array and instead use a map of which cubes are active, because it is always the case that an inactive cube with all inactive neighbors remains inactive, you can then just start with the active cubes and look at all neighbors of active cubes, and those are the only ones that could potentially flip from off to on. So in that way, you don't need to keep an array of every possible cube that could be affected at any point in time. Instead, you don't have to think about kind of 4-dimensional propagation delays. Instead, you just have to iterate through the map of all active coordinates and look at all neighbors of active coordinates and assess whether those should remain on, remain off, or flip states. So go look at that code and go look at that video on demand if you're interested. Okay. In day number 18, this was again a introduction to computer science techniques for people who had not seen this before. In particular, what you were expected to do for day number 18 was implement a parser that would parse a mathematical expression that uses different arithmetic rules than we do in real life. So in real life, we consider multiplication before addition, but in this problem, you consider addition before multiplication in your order in which you evaluate things. I know some people hacked around this by overwriting their language runtime to have star be plus and plus be star, and but use the mathematical results of doing the opposite thing. But that's not what I did. So that's what happens in part A. Or sorry, in part B. So as long as you implemented the parse tree, then you were able to relatively straightforwardly do this. But if you just computed these things, all right, part A was doing it left to right, and then part B you really needed that parse tree. Yeah, they're kind of were themes, right? Like as selfification points out, last year was VMs. This year was a lot of kind of parsing, a lot of state machines. Okay. So again, you'll see that day 18, I believe, was one of the days that some people got stuck on. Day 19. Is that correct? Day 18 we did. Yep, day 19. So day 19 took the notion of parsing up a level, right? Instead of you being expected to parse an input using the tools provided by your language runtime, instead in day 19 you were given a context-free grammar to evaluate and asked whether any given string happened to match that grammar or not. So in my particular case, I didn't convert these to regular expressions in part A, and that paid off for me in part B, because part B introduced the possibility of looping. I know some people address the possibility of looping by just copying out each of the copies until it exceeded the length of every available string. However, my solution would in fact work for an arbitrarily long string, which I consider to be really, really cool. So the thing that I did was I wrote matching rules that would take a given rule set and evaluate whether a substring starting at a given position could potentially be a match, and if so, it would return the rest of the string after the match prefix had been removed. And that was a method that allowed me to be able to evaluate character by character and always have kind of a base case and to build up from the base case. Again, kind of you see that notion of construct the base case, be able to solve starting from base case and then base case plus one rule, base case plus two rules, base case plus three rules, right? That kind of iteration makes it possible to solve what would otherwise be computationally intractable problems. So here you can see basically I constructed the idea that, either you had a literal string or you had a list of child rules that could potentially map. So if it was the literal string, then we just check the next character in the string, and then after that slice off everything else. Otherwise, you wind up having to recurse, and that's how I solve this problem. Okay, so now we go to day number, and again, like if you look at this, very, very, very sharp drop off. 7,000 people dropped off between day 18 and day 19. Day number 20. You just saw me solve this. I'm not going to talk about it at length. This was can you reassemble puzzle pieces based off of their edges, and then can you perform a search inside of that reassembled puzzle by rotating and flipping the pieces? And for me, I elected the initial wrong approach. in terms of trying to flip each piece, and do mathematical calculations and flipping each piece, when I should have just pre-rotated each piece. And that enabled me to get through it in 90 minutes when I came back to it a few weeks later. Okay, day 21. Day 21 was frustrating for me because it was yet another constraint solution. Like, it was literally just another constraint solution. The only difference to the constraint solving was that you had to have the realization that this prose here, of which ingredients can't possibly contain any of the allergens, was semantically equivalent to the statement, for each allergen, look for a food that is found in all of the recipes containing that allergen, and not starting from each individual recipe. Map it back to allergens. So a lot of people got tangled up in the prose, whereas I happened to be able to parse that and figure out, based off of the example, how was it that they were able to figure out that KFCDS didn't contain an allergen. Okay, and then after that, it was another one of those. You have 5 constraints and 5 items, and the first constraint matches exactly one thing. The second one narrows it down to 2 things, and so forth. All right, day 22. So in day 22, we started getting introduced to the crab and the crab's games that involve very, very large numbers. So this one was also a recursive game, similar to Scherzerad, the card in Magic, where you wind up not just playing war. 1, 2, 3, 4. I declare war, etc. With cards where the highest value wins. The recursive combat required you to evaluate some very, very carefully worded things that I missed initially. I think I failed to create the sub-deck. I was re-evaluating war on the same deck over and over and over again, rather than evaluating war on sub-decks, because you are only supposed to evaluate war on the on a finite smaller number of cards, and I was searching and searching and searching for my infinite loop, when my infinite loop was nowhere in the logic for the searching, or it was in the construction of the sub-deck. Okay, day number 23. Another day that tripped people up a little bit. I happen to know about Container Ring and Go, so this was pretty straightforward. The reason I knew about Container Ring and Go is that there is a previous puzzle, set of puzzles in a previous year involving, I believe, what was called knot hash, that involved knotting a loop. And the knot hash was basically very, very similar to this, where you were expected to slice elements out of a ring and then to resplice them back in. So this one basically, for me, involved using the ring class, which is effectively a doubly linked circular list. But if people didn't know about the ring class or didn't have it in their language, they implemented using single or doubly linked lists. And the trick here was that, again, like theme of the year, a lot of people were fence painting. A lot of people were searching through the entire loop to find out whether a value was present in it, or where the next copy of a value was, when you could instead store a pointer to the index in your array or a pointer to your list or ring, in order to skip directly to the element that's labeled n. And that way you could very, very quickly perform the splice rather than needing to step through one at a time looking for the place to perform this splice. So if you fence painted, you got a very, very slow answer. If you used the cached value, then the cached pointer, it was very, very fast. Day number 24. In day number 24, surprise, surprise, it is, again, a state machine, right? It is like the Conway's Law thing. It was like Conway's cubes. It was like the airport seats, except for, in order to figure out which seat you need to flip for your initial input, you need to evaluate a bunch of hex directions to travel in. which if you've done hex grids before, I used to be a game developer, so this was pretty straightforward for me. I was able to very quickly reproduce it from first principles without consulting a reference, but if you hadn't seen this before, you might struggle a little bit. There's a really interesting article about hexagonal grids that I would recommend people read if you're interested in kind of more of the general theory. Yes, I used to be a game dev. I was a game dev on Puzzle Pirates. So if you go to Wikipedia, you can see that I worked on Puzzle Pirates from 2005 until 2008. I was involved in some amount of puzzle design, but mostly system operations and banning cheaters from my game. So that's how I'd seen hex grids before, knew exactly what to do. And then after that, you're called upon to do Conway's Law on a hex grid. So, and then finally, date number 25 was Diffie-Hellman exchange. So it required you to have some knowledge of modular arithmetic, which you should have known from before. But I found this prose here to be absolutely impenetrable. I was 99% sure it was Diffie-Hellman, but I wasn't 100% sure. And for Diffie-Hellman, it doesn't matter what order the inputs are provided in, because it is a asymmetric crypto algorithm, but where it is agnostic as to which side is which, because you wind up with the same answer on both sides. But I spent forever trying to figure out which input corresponds to the card and which input corresponds to the door. The answer is it does not matter. It does not matter. And my solution ultimately wound up evaluating both just to check that they result in both the same value. Yeah, it's basically Diffie-Hellman, where you have your exponent, and then you have your public value. You perform the operation n times in order to you have the base of the exponent, that's a publicly known parameter. The value to which you exponentiate it is your secret, and then the value modulus at the end, that's your public key. So if you read about Diffie-Hellman encryption, that's basically what that is. And then after that, part 25b was, have you solved all the other puzzles, which I had, because I had in fact done day 20 the cheesy way. But now I can rightly, truly, and properly say that I have solved all 25 days of admin of code of 2020. And as you can see here, it means that I am in the 300 star club. I have solved every single admin of code puzzle. So this is where we end. Hey Vex. So thank you very, very much for tuning in. I may stream again in the future. It may be software development. It may be related to my company. So I work at a company called honeycomb.io. And we actually have a survey that's on right now if people are interested in doing it. So there is a survey that we're interested in hearing about. If you are a software developer, how do you debug your software? What's it like to run your software in production? So go check that out. We are at twitter.com/honeycombio. And if you go down here, I believe you will find the research. Where's the survey? Arg. From Honeycombio survey. There we are. So if you go here, do me a solid, do my company a solid, please take this survey about your software dev practices. We promise not to market to you if you fill out that survey. If you sign up for other things, we may market to you, but this is just, we're interested in hearing how people debug and what tools they use. All right, so I've been talking and streaming for 2 hours now. Thank you all very much for tuning in. So as I said, there may be Honeycomb-related stuff on the stream in the future. There may be other puzzle coding stuff, or there may be gaming, now that I have a little bit more streaming and gaming-capable computer. Thank you all very, very much. I've really appreciated your company, and if you are watching this for some reason later on YouTube, like, comment, subscribe, and stay safe out there. Middle finger to 2020. Let's hope that 2021 is better. Cheers, folks.